what we're going to learn about now is we talked a lot about the structure of our galaxy. We're going to start talking about other galaxies, and I've divided it into two sections. One is called normal galaxies, and then the next lecture is called active galaxies. The simple fact is that it's not a great distinction because normal galaxies are sometimes active. It's not that they're different galaxies. They're the same galaxies in different times of their life. So, but we'll learn about that as we go. If the page would turn, we'll do it. Okay. So we'll start talking about classifying galaxies, which you did a little bit in your tutorial that's due tonight. Keep in mind that there's a section there that you're supposed to be creative. So don't worry about like, oh, is it, the egg drop soup galaxy versus the lo mein noodle galaxy. That's okay. It's whatever in your imagination you'd like to do. It turns out, what you probably come up with for the different types of galaxies are going to be equivalent to what the astronomers did, but just with different names. So this is, I'm going to turn out the lights because we're going to be looking at pictures of galaxies, and they're kind of pretty, I think. Okay. So this is a galaxy, one of the largest galaxies in a nearby cluster of galaxies, and we'll learn about. Just like stars are in clusters, so are galaxies. And this galaxy is an elliptical galaxy. It's one of the largest in our neighborhood, in our local neighborhood of the universe. This one, we call it E. And E means elliptical. We're very imaginative. And 0 means it's round. Like the number 0 is kind of round. And as they get less round, we get higher numbers. We go from E0, 1, 2, 3, and so on, up to about 7. Now, one thing you'll notice about this elliptical galaxy is, well, it has that blue thing flying out of it. Do you see that? So this elliptical galaxy has an active nucleus. That jet coming out, and we'll learn more about that later, that line is a bunch of particles that are traveling nearly at the speed of light, almost directly towards us. So that's why it looks like that. So like I said, even when we talk about normal galaxies, we do confront. It's not unusual for a galaxy to be doing something like this. Maybe 1 in 10 or so will have an active nucleus. But we're going to spend a lot of time talking about those active nucleus in the next after we talk about normal galaxies. Is that your question? Yeah, I'm not going to just brush over it, but you see it, right? So it's quite cool. Like, I actually, in my research, used this particular galaxy to... Does anyone, maybe it's apocryphal, I think it actually happened, of the story of, Galileo climbs up the Tower of Pisa and starts dropping things and seeing how fast they fall. You've heard this story, and everything, unlike, what was thought, he realized that things basically fall at the same rate, and the difference is the air pushing back, depending on what their density was. So for this galaxy, in fact, we can use that black hole. You can see this jet. If I look right in the center, I can see where the black hole actually is, the base of this jet. And I can use the position of that hole to measure how black holes fall versus normal stuff, believe it or not. So black holes, it turns out, fall more or less like normal stuff. But it's the same sort of experiment as Galileo. But if Galileo had a bowling ball and a black hole, and drop them. If you want to know how, I can tell you all after class. But you can use that. I, in fact, did use that galaxy to measure how black holes fall. So elliptical galaxies, they go from being round to something about as flat as this guy. So this is called E7. And the way the numbers are defined is you take the longer axis and subtract the smaller one, divide it by the longer one, and multiply by 10. So you can see how you could get, like, if long minus short they're equal, you would get a 0, and something flattened like this, you get a number like 7, meaning, and we could figure out what that actually means, but I think it means it's about 3 times in one direction versus the other. So it's a 3-to-1 ratio, and that's sort of what it looks like. Now, you could ask, could there be E8, E9? There could be, but we don't see them. So what happens is we can sort of understand what's making them flat, but if you want to think about galaxies that are flatter than this, what typically happens is you end up getting a disk and a round thing in the middle. That's just more stable than making it even flatter than this. So in that picture, right, we see this galaxy, but you also see, lots of other galaxies there that are quite pretty, like this galaxy. And that's obviously a different type of galaxy. And this galaxy up here is doing something different still. So we have the elliptical galaxies. And then if we think about, and this isn't the greatest example because I can see it has some dust in it, but we have galaxies that are like a spiral galaxy in all except they don't have any spiral arms. And in fact, they have very little dust. Here, we're looking at this galaxy precisely edge on, so even it has a little bit of dust in it, but nothing like our galaxy. Think about, like, if we look in our galaxy, the dust is blocking out a huge amount of light. This galaxy, we call it an S0. So it's a galaxy that has a disk and a bulge, but it doesn't have very much gas or dust. And that's important. And these galaxies don't have spiral structure. So if you look at them face on, you can see this. They look like a fried egg, if you see what I mean, like a sunny side up egg. They're quite flat, and then in the middle, there's this bulge, but there's no, like if I gave you an egg with spiral structure in it, you probably wouldn't eat it. But these guys, you just imagine them like a sunny side up egg. They don't have any spiral structure. So here's a very pretty spiral galaxy. This is imaginatively called the Whirlpool Galaxy. I think it's also M81, Messier 81. So here we see a very dramatic spiral structure. This we call a grand design spiral because you can trace those spiral arms out for, like here, this is 1 rotation, almost 2 if we made it go further. So like here we go, start there, we go around once, almost twice. So that's unusual for us to see in a spiral galaxy. Now, you may ask, what's this thing? That's another galaxy. Now, galaxies are really, really close together compared to stars. So galaxies, it's very common to see galaxies interacting with each other, and it's very common for one galaxy to eat up another galaxy. And in fact, our galaxy right now is eating up another galaxy that's much smaller than it. So here, this is 2 galaxies. The second galaxy is quite a bit smaller and less massive than the first. And you can ask, it has this beautiful spiral structure. Does that have anything to do with there being a second galaxy? And it does. So this having a second galaxy near spiral galaxy will make the spiral structure much more pronounced. It just induces there to be spiral structure. But this also gives you an idea, looking down on this, how stars form, right? And it's quite interesting. I don't know if wow, there is a lot there to take in, right? So let's imagine this galaxy is the spiral arms are going like in this direction, like anti-clockwise, which is what it looks like, right? Like a sprinkler. You don't know whether it could be spinning the other way, clockwise. That's something you have to measure, and we know typically they spin. They spin so the spiral arms are trailing. Okay, does that make sense what I'm saying? Okay. But if we look in detail here, we can see something cool. So like over here, we see the dust lane is over here, and then there's new stars on this side. In this part, the dust lane is here, and the new stars are on the other side. Do you notice that? That the two arms are kind of reversed relative to each other. Now, if you remember what we talked about with all the stars go around the galaxy at the same speed, but the spiral structure, we think, rotates at a constant angular rate, so it is maintained. So like the spiral structure, if I were to look at this later, would have just rotated, the whole thing would look the same. But the stars go in and out of the spiral arms, right? And the gas does. So what's happening here is gas flows in, gets compressed, we see the dust lane, and it catches up to the spiral arms, and we form structure on the other side. Over here, the spiral arm catches up to the gas, it gets compressed, and forms stars the other way. Does that make sense? So, like in this picture, you can see, with some imagination, or guided imagination, the stars that are towards the middle of the galaxy go around faster than the spiral arms, and the stars on the outer side go around slower than the spiral arms. So it's a really amazing picture. So these big red things here are huge regions of star formation. This is a much more actively star-forming galaxy than our own, and it's because all the gas is being disturbed by that galaxy over to the side. That's why it looks so amazing. And those red blobbies there, in the future, will be objects essentially like globular clusters. There'll be millions of stars born in those little regions. Yes?
What wavelength is this?
Oh yeah, this is what it would look like to your eye. So the red color is hydrogen gas. We call it hydrogen alpha. So it's that red is around 656 nanometers, around there. It's something you perceive as, we've not doctored with the color. This is sort of in natural color. Okay? So here's another type of spiral galaxy that looks a bit different. Wow, it was worthwhile shutting off the lights. This is a barred spiral galaxy. So you can see the central region, we have a region of stars that essentially looks like a bar. The bar is different from the bulge. There can be this sort of roundish thing is the bulge. And then look here, you see these lines, right? All the dust is lined up. This is one part of the bar, another part of the bar, and then the spiral arms trail off the end of the bar. Again, this guy is forming stars quite dramatically. Wow, it's pretty. I'm just going to look at that a little bit. You can see, this is a deep image, and you can see, there's galaxies. The sky is absolutely full of galaxies. So wherever you look, right, there's galaxies behind the galaxy that you're looking at. But that's an amazing one. So here, this is just a different way a galaxy can go. So this is a barred spiral. Its spiral arms are quite loose, right? They're quite loose. The last type, another type of galaxy, we call that, if we look at the Magellanic Clouds, and this is a picture of how it would look. I would say this is how, if you were in a relatively dark place in Australia or in the southern hemisphere, this is how it would look to you with your eye once you've adjusted. So that's the Large Magellanic Cloud up in the right. The Small Magellanic Cloud is in the left. That bright thing here next to it is a globular cluster that we talked about, 47 Tucanae. So let's zoom in on the Small Magellanic Cloud. Again, this is just with what you would perceive with your eye. I've just zoomed in on the previous image. This is the Small Magellanic Cloud. It's just kind of a mess. It's quite messy. In reality, in three-dimensional space, this guy is quite long. So it's like, you could think of it as like a long cylinder, and we're looking down the cylinder, it turns out. So it looks quite messy here, but it is pretty messy. The Large Magellanic Cloud, if you have enough imagination, you can imagine it has a bar and maybe one arm of a spiral. This is, again, not a very deep picture, but there's hints that it has a bit of an arm. So one thinks of the Large Magellanic Cloud as sort of a hopeless spiral galaxy, a very extreme one. So if we look at how we think about these different galaxies, it's we call this the morphological classification of galaxies. And morphology just means shape. So we're classifying them based on shape. This is like called the tuning fork. There's no sense that the galaxies move along this in different ways. It's not like the HR diagram that we saw earlier. It just really helps us think about what they look like. So if we start on the left, we have elliptical galaxies. The elliptical galaxies that appear round, we call them E0. Now, no one asked the question, but what if it's a galaxy that's shaped like a cigar, let's say, and we're looking down the length of the cigar, then it would appear round. We would call that E0. This is just on the basis of what we see. In reality, that E0 galaxy could be like something quite flat, and we're looking at it in the right way. Do people understand what I'm saying? So as we go over, we get them to be flatter and flatter, E0, E3, 5, 7. And then we don't see them any flatter than this guy, and the next type of galaxy that we see are a bit more flat are the S0s. And that's a better picture of an S0. It really does look like a sort of sunny side up egg. We don't see any hint of dust there. We don't see any hint of spiral structure. So as we go further along the sequence of spirals, if we look on the top, what we see is that the spiral arms, they get more tightly wound, we say. Sorry, that's just kind of a weird way of putting it. But as you look at the spiral galaxies towards the left, they typically have a larger bulge compared to the disk. Their spiral arms are sort of a bit tighter. As we go towards the other spiral galaxies up on the top sequence, what you end up seeing is you get to see more spiral arms. They can be less tightly wrapped up here, right? So they're looser, but you see more of them. Another way that we call about these guys, and I don't know exactly what it means, is called flocculent. There's lots of great words that are pretty words that have to do with galaxies. So flocculent means that you see lots of this swirly structure, but it's very hard to trace a spiral arm all the way around. So as we go towards the, we call them later spirals, the spiral structure becomes more flocculent, as it were. These galaxies down this side are the ones with the bars. They have a bar, so the bar already makes the galaxy have this symmetry, and typically the bar galaxies have just two spiral arms coming off each end of the bar, and as you get smaller bulges, you can see this is the bulge, smaller, smaller, the spiral arms become less pronounced, more flocculent, as it were. Another nice word is with these galaxies, which sounds really fancy. It's called a lenticular. They're called a lenticular galaxy, which lenticular means shaped like a lens. But if you look at the root of it, it means exactly what it sounds. The word for lens comes from the word for lentil, which is a type of bean. So these are shaped lenticular. They're shaped like a lentil. The word lentil is right in there. We have these fancy words, but they're basically just descriptive. So what we can do is we can get an idea of the physical properties of these galaxies here. So if we think about the spiral galaxies, they have a range of mass of just about a factor of 1,000. So they start out, around 1 billion solar masses. They can go up to 1 trillion. That's the mass of everything, including the dark matter. Okay? The luminosity, how bright they are in terms of the sun, is about 1/10 of that mass. So their mass to light ratio is 1/10. It's 10. So they go from 100 million times what the sun is like up to 100 billion. Now the key thing is so we can see all these things. The spirals have young stars and old stars. They have a mixture of population, and they have gas and dust. So the gas is the raw material to make stars. And the dust also helps. It's maybe a catalyst to making stars. So without gas and dust, you don't get star formation, and that goes hand in hand with the fact that they have young stars. Now, if we go to the elliptical galaxies, they have a much wider range of sizes. Instead of this factor of about 1,000 in mass, they have a factor of a huge amount, over 1 million, right, in mass. If we look at luminosity, it's also about a factor of 1 million. Their sizes range by a factor of 100, whereas for the spirals, it's just a factor of 10. So ellipticals, there's a wide variety of elliptical galaxies. We saw a picture of that M87, an absolutely massive elliptical galaxy, on the top end of that range. But there are also elliptical galaxies that are in orbit around the Andromeda galaxy that are towards the small end of that range. There's a wide range of elliptical galaxies, and that's a bit of we have to think about how that works. The stars in ellipticals were typically born a long time ago, and that goes hand in hand with the fact that they don't have any gas anymore, or very little gas. So we don't see stars forming in ellipticals. The irregular galaxies are typically smaller, right? And less luminous. They typically have lots of gas. So they're gas-rich compared to the other types of galaxies. So what makes them irregular is they're generally forming stars quite actively in different parts of the galaxy. It's not very well organized, so they look irregular. So let's just look at, this is now looking at the spiral galaxies a little bit. So this is not our galaxy. This is another galaxy, NGC 7331. And we see the same picture in a spiral galaxy that we see in our own galaxy. So the different parts of the galaxy, how fast they're going around the center of the galaxy, are given by the points at the top, right here. And you can see it's nearly flat, just like in our own galaxy, except here the measurements are now extending out to 40 kiloparsecs. So, well, this is physically, we can measure it further out in our than in our galaxy. Now, if you look at the different parts of the galaxy and how they make up this rotation, thinking about the parts of the galaxy that we can see, let's see, here's the gas, so the gas doesn't make a big deal. This is from the central region of the galaxy, the bulge, and the disk, which builds up in mass a bit slower. But you can see all of these components aren't enough, that you need at least beyond a few, around 10 kiloparsecs or even closer. You need an extra component that here's called the halo. That's the extra bit to account for when you add all of these up. You get the curve that goes through the points, right? So when I look at other spiral galaxies, I also see evidence for the dark matter. That other spiral galaxies, not just our own, have dark matter halos. It's kind of obvious, but I do need to tell you. It could have just been weird. But every spiral galaxy, we see rotation curves like this, not just our own. So one way we could, if we're looking at a spiral galaxy that's far away, maybe we don't get to see how it's rotating every little part of the galaxy, and what we measure is the spectrum of the entire galaxy all at once. And I can show you what that looks like, help you visualize it. So if I were to look at this galaxy from, this is the same galaxy, M81, it's so pretty. If we were to look at it from the left, if I look at the top part of the galaxy, it's coming towards us. So that radiation is blue shifted up here. And if I look at the bottom part of the galaxy, it's moving away from us. It's red shifted. Now, if we imagine, if I'm looking through the top up here, it goes through a lot of material that's all moving at the same velocity coming towards us, right? Because we're on this part of the circle. And similarly on the other side, it's all going away from us, but more or less at the same rate. In the middle part of the galaxy, we have material that's not moving so fast. It's intermediate between these two, and there's sort of less of it. It's more spread out in velocity. So if we add those three together, if we couldn't resolve the galaxy, we measure a spectrum, we would add them three together, and what we would get is sort of something that was humped, like a double hump thing, right? Where it comes up, and then it goes flat in the middle. And what we can do is we can measure the width of that hump, the width of it, and that's going to be related to how fast the galaxy is spinning. In fact, the width of that, if the galaxy is perfectly edge-on, is twice the rate of the spinning that we see in the rotation curve on this page, right? So if we were to look at this galaxy in the way that I described, we would find that those two humps would be 500 kilometers apart per second, because we have 250 plus 250. So we noticed something interesting about this. So this is what that galaxy would look like if we were to add everything up. The one I showed you earlier. You can see it has this double humped thing, and we want to measure the width of it. And the width of it is related to how fast the galaxy is spinning, and whether we're looking at it like this, edge on, or face on. Right? Here I wouldn't notice anything in terms of the Doppler shift, whereas here you would. So for this galaxy, whatever, we don't know necessarily what the inclination is. We can estimate it by what the shape it looks like on the sky. But what we can do is we can figure out for a whole bunch of galaxies how fast they're rotating, right? And what's interesting about that is as we look across the different spiral galaxies, how fast they rotate is put on the vertical axis, and how bright they are is on the horizontal axis, their magnitude. And all of these galaxies are in the same group called the Ursa Major group. I think it's, in fact, the group that has that pretty galaxy in it. And if you look at them, the galaxies that appear brighter rotate faster. You can see that. As we go to the right, things have smaller magnitudes, so they're brighter. Look what the magnitude is. It's like 6, 8. These are things that you can see with an amateur telescope, these pretty galaxies. It's a relatively nearby group of galaxies. So, but this is now, we're getting a sense of there are some relationships in galaxies, like between how bright they appear and how fast they're rotating, right? And that's maybe a little bit of a puzzle, because if you remember, what is accounting for how fast the galaxy is rotating? Not the light, not the stars. It's this dark matter. But somehow, the light and the dark matter are correlated in a way. The galaxy decides to form a given amount of stars depending on how much dark matter it has. So it's weird. Do we understand it? Not really. Not even yet. But this is a relationship that's quite useful, because now if I measure how fast the galaxy is rotating, I can get an estimate of how bright it is, and then see how bright it is inherently. And then I look at a distant galaxy, and I can measure how much further it is away from us than this group. So we're doing the same thing as you could do with stars. You did it with, in your tutorial, you had 2 star clusters. And on one axis you had color, and then how bright it is. Here, for galaxies, it's not color that we look at, how fast they're rotating versus how bright they appear. There's a nice correlation, and we can use that to measure the distances to galaxies throughout the universe. And if we look at what this correlation looks like, is that if I double the rate of spin of the galaxy, the luminosity goes up by 16. So very fast. So galaxies that are quite faint, they're over here, are spinning, this is a factor of 10 in how fast they're spinning, but it's almost 10 magnitudes, which is a factor of 10,000 in luminosity. Okay? So that's one first correlation that we see about galaxies. The second correlation involves not how individual galaxies, how bright they are compared to how fast they're rotating, but if we look at galaxies out there and can estimate their distance either from stars within the galaxy or perhaps from this Tully-Fisher relation, what we can do is we can ask, how far away are galaxies and how fast are they moving toward or away from us? And what we find, or people started to find in the 1920s even, is that every galaxy, except for maybe 3 or 4, are moving away from us. Every galaxy, except for very few, are moving away from us. So the ones that are moving towards us are, in fact, the Andromeda Galaxy and its coterie of satellites are moving towards us. I have a feeling this Ursa Major group that we just were talking about is also moving towards us, but everybody else is moving away from us. Once we're beyond the very closest galaxies, every galaxy is moving away from us. And in fact, as the galaxies are further away, they're moving away faster. So this is called the Hubble law, right? So the rate at which galaxies are moving away from us is proportional to the distance from us. Now, what does this have to do with? We'll learn about it later, but this is one of the basic things that has to do with galaxies. So galaxies almost universally are moving away from us. Basically, like for Hubble to figure this out, they had to find the distances to galaxies, and they had to measure their velocities, right? So when they started, they used the first galaxy that we actually measured a distance to that was beyond like the Large Magellanic Cloud was Hubble measured the distance to Andromeda using these Cepheid variables, which are variable stars that we saw a lot of them in the Large Magellanic Cloud, and the Cepheids in Andromeda are appear much fainter than those in the Large Magellanic Cloud, which told everyone at that point that this Andromeda galaxy was indeed the same size as our Milky Way galaxy, just 2 million light years away, instead of being some small object that's orbiting our galaxy. So once this happened, that told people that all of these things that look like Andromeda in the sky, and there were thousands or millions at that time, were galaxies like our own. Okay? And as you looked out, people have followed this going further away. So this is looking at a galaxy in the Virgo cluster, which is further away. But let me just try to think about it in light years, which is difficult. I think it's about 20 million light years. So it's 10 times further than Andromeda, which means the Cepheids are 100 times fainter. And you look in the galaxy, this is with the Hubble Space Telescope, and really that is the Cepheid in Virgo, right? It's that little smudge that gets brighter that they've noticed in there. But what that does is now tells us where this cluster is relative to us, how far away it is, right? So this is a step in the distance ladder. And then when you look in the Virgo cluster, we can see that there's lots of galaxies there, spiral galaxies, and we can measure how fast they're spinning. And then we can know, we can test that relationship between how fast they're spinning and their brightness. And we now know the actual luminosity of those galaxies in Virgo. And we can use that to go further away and use the galaxies as a standard candle. But let me just show you how essentially right now one measures distances in astronomy moving out from things in the solar system. And this is a complicated picture, and the boundaries are changing all the time because we do better jobs of it. So within the solar system, the basic distance upon which everything else in astronomy gets based is the distance between the Earth and the Sun, right? That's the astronomical unit, right? And how we measure that nowadays is by bouncing radio waves off of other planets, in particular, usually Venus. So if we bounce radio waves off of Venus, we can figure out the distance to Venus in meters or centimeters or whatever, and then we know from the orbit of Venus how big the orbit of Venus is compared to the Earth's orbit very accurately, and that gives us the size of Earth's orbit very accurately. We can also we have satellites that go around the back of the sun, and we can measure the distance there very accurately as well. And I suspect nowadays that might be the most accurate measure of the astronomical unit is from a satellite called Cassini, which went out to Jupiter and then to Saturn, but while it was near to get out to Saturn, it went round and round near the sun several times. So we could see it go in that orbit and measure its position very, very accurately, effectively with radar. So once we get the distance between the Earth and the sun, which is known to whatever, a centimeter or so, we can look out at the nearby stars and use the Earth's orbit, which is what we talked about, as to measure parallax. So that will tell us the distance to nearby stars relative to the size of Earth's orbit. And the big error in that is now not the size of Earth's orbit, but how well we can measure those angles to define the parallax. As this is written, you can see, it's kind of difficult, but it looks like parallax, you can go out to hundreds of light years. Parallax. With the satellite now called Gaia, maybe you can go out to almost maybe 3,000 light years measuring parallax. So what happens next is, if we have a whole lot of stars that we know distances to, if we're lucky, if we're not lucky, we can just make an HR diagram for those stars. And we can measure luminosity as a function of temperature, define where the main sequence is. And now I can look at another group of stars further away, like in a cluster, and you did this exercise where you had two clusters and you measured their magnitudes and you assumed they were the same type of stars so that you could shift one to be on the other. And that told you the relative distance of those two guys. You did that in tutorial 3, the really hard tutorial, we'll call it. And that's what we call main sequence fitting. And you did it. You did main sequence fitting yourselves. So that's the key, like measuring lots of interesting stars with parallax. In this step, we still need to use, but if one moves this green further out, which we're doing with Gaia, we can pick up some of these, or lots of these variable stars called Cepheids. They're quite rare. They are just a stage in the life of a very massive star. It's not the entire life of the massive star. It's only a stage. So you think massive stars are rare, and it's a fraction of their life that makes them especially rare, these objects called Cepheids. But once you have them, you can measure, if you measure their period, you can infer what their luminosity is. Okay? So if you have a whole bunch of them nearby, that helps us to understand that. It is complicated, but I'm not sugarcoating it. Then, like we talked about what Hubble did, people are still doing this. They look for Cepheids in distant galaxies. Unfortunately, these Cepheids, even though they're in distant galaxies, those galaxies are close enough to us that the gravity of all the galaxies between us and them and the group of galaxies that they're in affects their velocities a lot. But what that does is give us distances to a bunch of galaxies. And in those galaxies that we have distances to, if we're lucky, there's been supernova. There are a lot of steps. Supernova have been found that, again, they have a relationship like Cepheids, that the time for the supernova to get bright and then faint again is correlated with the luminosity. So now if I look at a really far away supernova and I measure how long it takes to get bright and faint, that tells me the luminosity. And then if I know how bright the supernova appeared, that tells me the distance. Yes?
Wouldn't redshifting make that harder because it would also change the amount of time?
Absolutely, but it doesn't make it harder because you know the redshift. So you just correct for it. But that's the thing, right? So you're watching it getting brighter and fainter, right? And then you have to go back and say, well, how long did that brightening and faintening take from the point of view of the galaxy? And you have to include that in your calculation. So like, let's say it gets brighter and fainter, and we observe it to take 20 days to get bright and faint, but it's at a redshift of 2. No, redshift of 1, just let's make the math easy. That means from its point of view, it took 10 days. And then I take the 10 days, and I look at a nearby supernova that went up and down in 10 days, not in 20. 20 was what we observed, but we have to deal with the redshift, just like you said. And we find one that went up and down in 10 days. Let's say it's in galaxy whatever, M101, just for argument's sake. M101 has a Cepheid in it, or 2, so I know the distance to M101. So I know now the distance to that galaxy at redshift of 2 relative to Messier 101, and I know the distance to Messier 101 because of the Cepheids. And that's called the distance ladder. And that's one of these things that we know from the very beginning of the course, that measuring distances is crucial to understanding everything. Because if something's twice as far, generally it has to be 4 times more energetic. So when we move galaxies, when we make the universe bigger, everything, all the energies get much larger. And, it becomes astronomical, right? As it were. So what we do is we measure lots and lots of these type 1a supernova, and we can get a sort of picture here of now the distance along the top is this way, and I've cut it out on the bottom. So that's the log of the distance, and on the other way, it's the log of the redshift. So you can see when the galaxies are nearby, these are small distances, let's say 10 megaparsecs or so. I can see Cepheids. So these are these round circles, right? And then as they get further, you can see I have this one here with the dark circles. Boop, 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 boop. That says TF. Does anyone remember what TF is? I told you. It's okay. No one remembers? That's called Tully-Fisher. Means that the galaxies that spin faster are brighter. So here is we look at nearby galaxies over here. We know how fast they're spinning. We know their distances. So now we can find a galaxy that's further away, who's spinning just as fast, and use that galaxy, how bright it appears compared to a nearby one. That now tells me how far away that galaxy is, okay? That's what TF stands for. There are other symbols there. One is FP, which I didn't tell you about. Those are triangles. That's a relationship between, in an elliptical galaxy, how bright it is and how fast the stars are moving. So it's almost the same idea as Tully-Fisher, except elliptical galaxies don't rotate. They're just like a swarm of bees, and the stars are moving in all sorts of directions. There are other ones there too. There's one that's a diamond, which if you're interested, I can explain. But then there's the square, which I guess there should be a lot of squares. Yeah. There's squares in this one, which are kind of further away. You can see these squares. And those are the supernova, right? So the most accurate ones that are far away are the supernova. And you can see that there's a lot of them, right? Up here there's supernova, and here there's supernova. And now we have distance on one and velocity on the other line, and the slope of this line is the Hubble constant that we talked about. Well, actually the normalization of that. The fact that it looks like a straight line with that slope means that distance is proportional to velocity. Okay, so this is where things get left, right? This is the best that people have done so far. It's just when you start to look really far away, this is a redshift of 0.1. When you look further, it's no longer a straight line. And that was what people were trying to measure, right? With more and more distant galaxies, this line starts to curve. And we'll learn more about that when we talk about cosmology. But the big surprise around 20 years ago was this line was expected to curve, in this sense, I think, to curve upwards, but it actually curves downwards. And we'll understand that, but that discovery won people a Nobel Prize, which told us that we understand even less of the universe than we thought we understood up to this point. So right now, our inventory is that, we have about 10% or less of what the universe is made of is this stuff we're familiar with from Earth, and then 90% is this dark matter. When people started examining this, they realized, in fact, no, 3% is what we know about 30% is dark matter, and then the remaining 70% is something that we really, really don't understand, that we call dark energy. But this is foreshadowing.